The offspring have genotype that is not like the parents.
Is which one? Recombinant?
Recombinant.
Yeah. So in our example, what was the last thing we did? We had to make a table of how many of each characteristic, was there? Like how many purple long, how many... Yeah. Do you have that table? I can just copy it down there. I didn't... It's just, or if you have your own table, do you have one of these?
You mean this table or which?
The one where I think we had... Can I see? I can show you which one. State the number of observed recombinant. Yeah, so it's the table with the observation. There we go. So it's this one here. So if I just copy something like this down. So what's the first one there? Is that big P, big L?
Yeah.
Okay, so that's this. Okay, and what was the expected and the observed?
Expected was 214.3.
Okay, I'll just say 214. You should say 0.3. And the observed for you, what was it?
283 for me.
283. Okay, and then what's the next one?
Big P, little L.
Big P, little l. Okay, and the two numbers?
71.4.
71 and
22.
22. Okay, and the next one?
Little P, big L.
Okay.
71.1.
71. Yeah.
And 20.
Okay, and the last thing must be small and small.
23.8 and 56.
Okay, so this is just the example we use. Okay, so or that's the recombinant, and in this case, which ones are we adding together? So which one were the parents? Parents were the pure breed, weren't they?
Yeah.
Is only this one the parents?
No.
No? Which ones are the parents? Purple long and... Oh, this one and this one, is it?
Yeah.
So are these two are the OR, is it? Yeah?
Yeah.
Yeah. That's now, see, Colin was explaining this to me yesterday as well. Is that what you would all agree with? So this one is 42 in my example. Yeah? Would you agree with this? Yeah? So then the NOR, that would have to be 283 plus 56 in my example, yeah? So what's that? 339? Yeah? Now, please don't do that thing where you're just saying yeah and agreeing with me because you think I'm right because I'm the teacher or something. I don't know this, so I'm trusting you and your understanding from Colin that this is correct. So we're going with this then? Yeah. Okay, so what's the next part now? So this is still task 2. State OR and NOR. Based on your data, state the probability of recombination. Okay, so in this case here, that would be P would equal, so how many of them recombinants? It's 42 out of 42 plus 339. So in this case, it's 42 in 381. That's the probability of a recombinant. It should be pretty small because most of what was observed was non-recombinants. Is that normally what happens in genetics, or I don't know? Or are we talking too much about things you don't do in biology? Is it this kind of normal that mostly you get non-recombinants and only sometimes you get recombinants?
Yeah.
That's a normal thing to be happening, yeah. So this, what is this as a decimal, please? It should be pretty small. Minus? Couldn't possibly be minus. Okay, well 42 over 381. Yeah. 0 point. Oh, okay, 0.11? Okay, right. Right. Well, that's okay. Now the last thing in task 2, discuss your findings. Alright. So what has task 2 taught us, other than maths teachers don't know much about genetics? What have we learned from task 2? Did we do everything in task 2? Yeah. So we did the chi-squared. And what was the result we got from the chi-squared? Accept or reject? Do you remember? Was it accept? I thought it was reject. Yeah, the critical value was something like 7, was it? And what did we get? Oh no, but that's from the table book. What value did we get?
We got like 137.9.
You've got a huge number. Yeah. So we rejected the hypothesis. And what was our hypothesis? That
If it was the ratio.
that it was a ratio of
9331.
9331, yeah. Which is the ratio you would expect under Mendel's theory,
Yeah.
of genetics and the Punnett square. So, what have we concluded from task 2? That we can reject the ratio, we reject the ratio, no, I won't get my grammar right. Reject Mendel's predicted ratio for the, what are these called? Characteristics or traits, or is that what you'd call traits? Is it purple and long and round? Yeah. So anyways, the conclusion for task 2 is we reject this ratio according to Mendel's theory. Yeah. Okay, 133 or 9331, wasn't it? Yeah. Okay. Right, so that's task 2 complete, the hypothesis test. So now on to task 3. Morgan discovered that chromosomes positions affect the probability of recombination. Morgan noted that. Okay. So in our experiment here, recombination is kind of small probability, 0.11. And what Morgan discovered is that this probability, it actually depends on how far apart, what's it called, something is on the chromosome, base pair or something?
The
Or
locus.
the locus, that's the word, very good, thank you. How far apart the locus is on the chromosome. So, if you knew how far apart the loci are, then you can calculate the probability. That's what Morgan said. So, find the value of p if the distance increases to infinity. That is, if the distance becomes extremely large. Okay, so let's calculate that. So that's 1 minus e to the power of minus infinity all over 2. Now there's a problem with this. You can't really put infinity in on the calculator. So if you don't know what e to the power of minus infinity is, you could try and roughly work it out by just putting in on the calculator 1 minus e to the minus a very large number, like a billion or a trillion, and you can get the answer here. So if you want, you can test it, but if you know what e to the minus infinity is, that's great. Do you know what it is?
No.
No? So what did you get if you put in e to the minus a large, 1 minus e to the minus a large number all over 2? I hope you get something that is close to this. Now you can check it out. Something close to this? No? Yes? Oh, you left out your, I didn't see you typed in the E. Do you know how to get it on the calculator? You don't see where it is? I think it's on the top right. Yeah. Yeah, yeah. What did you use as your large number? 1 million, okay, good, yeah. Not quite as much as infinity, but close. Yeah. Okay, so think about what this means, what Morgan is saying. Morgan is saying that if the locusts are very, very far apart on the chromosome, what's the probability of a recombinant here? 50%. Yeah? I think this is the same thing Mendel was saying as well, that recombinant probability is 50%. Because I think obviously Mendel didn't really know about chromosomes and all of this, but I think in his understanding it's always 50%. But really, as Morgan worked out, actually it depends on how far apart the locus is on the chromosome. So if they're very far apart, yeah, it's 50%. But if they're not very far apart, then it's not 50%. And the example we just did today, in our example, is actually 11%. So these traits, these locus must not be that far apart from the chromosome then. Yeah. Okay, so let's see the B part. Using your probability, calculate the distance between colour and shape. Okay, so in this example we have to work backwards. We got 0.11 and we need to figure out what the D is. Okay, now this equation, we need to solve this for D. So what could we do to try and solve this? How could we rearrange this? Cross multiply first, yeah. So I get 0.22 equals 1 minus e to the minus 2d over 100. Okay, what should I do next now? What do you think? I think I'll bring the e to the left and the 0.22 to the right. So I get e to the minus 2d over 100 equals 1 minus 0.22. That's 0.78. Okay, now what should I do next? That's it. ln. And what happens? Why use ln? What does it do? Yep. Moves the e, yeah. So you get minus 2d over 100 equals that. What's log 0.78? ln 0.78. Yep. Okay. So finally, or nearly finally, you get d is going to be, if I cross multiply and divide by 2, I get 10.79 over 2. What's that now? 5.4, isn't it? Roughly 5.4, isn't it? Yeah. I know it's not exactly, but just roughly 5.4. That's 5.4 Morgans. That's how you measure the distance here. Although I was being a little bit sneaky, I said in the question, use centimorgans. So how many centimorgans in a Morgan do you think? Yeah, now think about where else you know of centi. Where else do you hear centi? Centimeters. So how many centimeters in a meter? 100. So how many centimorgans in a Morgan? 100. So 5.4 Morgans would be 540 centimorgans. 540 centimorgans apart. Now I don't remember, I didn't say it here, you might have to look it up, but I think a centimorgan, I think a centimorgan is 1,000,000 base pairs. I don't know. You can look it up. I saw it on Wikipedia. So, anyways, I can't remember. Maybe a Morgan is 1,000,000 base pairs. I'm not sure. So you can convert this into base pairs if you like. Right. Next one now. So that's B. C. By using the binomial distribution, calculate the probability of observing N-OR recombinants and N-OR recombinants. Okay. I have to write my numbers down from earlier. Where's it gone? Okay. So, OR is 42, NOR is 42 and NOR is 339, and the P is 0.11. Okay. Do you remember the binomial probabilities? Doing this in class? What type of problems do you use binomial probabilities for? Can you give me an example? What type of situations? Do you know? Can sometimes have a large number, yeah. But what type of events are you looking at? You know what I mean? Like what type of situations, what type of events, what type of outcomes?
Like if it's going to rain or not going to rain?
Yeah, that's it. Like you're looking at like one or the other situations, like rain, not rain. They vote yes or they don't vote yes, you know. Heads or tails, this type of thing here. So that's kind of what you have here. You can have recombinant or not recombinant. So the question I ask you to do is calculate the probability of getting this many recombinants. So the formula is in the formula book. So I'm not going to draw it obviously, but it's going to be like 1, 2, ... all the way up to 381, I think is the total. Okay. So if you were to look at all of these plants that you have, how many of them were recombinants? 42 of them were recombinants. And how many of them were non-recombinants? 389. Yeah? Can you see how this is a lot like the problems in class where you said 10 people vote, or what's the probability 6 people vote yes and 4 people vote no? Or you flip a coin 10 times, what's the probability you get 7 heads and 3 tails or something like this? This is a binomial problem. So the formula is in the formula book. It's 381C 42 because you want 42 successes, or in this case recombinants, and then you have the probability of a recombinant to the power of how many recombinants, and the probability of not recombinant, which if it's 0.11 then not would be 0.89, to the power of what? What power it goes here? Yeah, 42 went here, and this one would be, yeah, which is 339 in this one here. Yeah, 381 minus 42. Yeah? Now, we have to calculate this. I don't know if your calculator can calculate it. You've already tried typing it in already? Can your fancy pants graphing calculator calculate this? Huh?
Yeah, John recommended a website, Wolfram Alpha.
Very good, yeah, I was just going to say, if your calculator can do that, it's very impressive, but there are websites that obviously are more powerful than your calculator. You can type this problem, you can type this into Wolfram Alpha and it'll give you the answer. Okay, so they have like a search box, so you would type it in as something like 381C42 and you would put that in brackets. And then how do you type a multiply on the keyboard? A star, and then you would type in 0.11, and how do you type a power on the keyboard, you know? That thing, yes. This thing, 42, star, 0.89, power, 339. And you put this in, and I think it gives you an extremely small number. I don't remember what, but I'll just say it's something like you get the probability is 10 to the minus 42, or something really, really, really small, like this. Yeah? Okay, good. So that answers part C. Now, part D, I ask you to do exactly the same thing, except this time using Mendel's probability of recombination, which is 0.5. In fact, not that I forgot to say, that didn't really come up earlier, but when you say the probability is 0.5, that means the two loci are extremely far apart, which actually means that they're on separate chromosomes. Yeah, because I mean, they can't be on the same chromosome if they're like infinitely far apart practically. Okay, so let's, I want you to do everything again, except this time use P as 0.5. So the only difference is 381C42, 0.5 42, and 0.89, sorry, what am I saying? 0.5 339. Yeah? And again, you can put this into Wolfram alpha and you'll get a different answer. I think you get a bigger answer. I can't remember what it is. I'm just going to make up a number. I think maybe you might get something like 10 to the minus 32 or something. I don't know. I don't have Wolfram open, but whatever it is, you can calculate it easily. Okay, that's part D done. Part E, you have something called the linkage between flower color and pollen shape can be tested for by calculating the log of odds, the lowest Z score, and the formula is there. Calculate it for your problem. Okay, so let's calculate it here. So this is what task is E. So Z is equal to log base 10, and on the top you get the probability you first calculated, which I think I said was 10 to the minus 42. And then on the bottom you get a probability if you use 0.5, what do you get? And in my example I made up, I got 10 to the minus 32. Or whatever it is. Okay, so if you hit this in on the calculator, I think you'll get something like minus 10, I think. Now that's log base 10, that's log, yeah. 10 to the minus 10. Yeah, you get minus 10 here, don't you? Yeah. Yeah. Okay. Now, last part. So, this is where we kind of complete this task and put everything together. Morgan said that the further away locus are, does that make it more likely or less likely for recombinants? The further away they are. I think we said more likely because when we said they were very, very far apart, what probability did we get? 0.5. Yeah, and in our example, what was the probability of recombinant? 0.11. Okay, so if you get an answer of 0.5 or near it, then it means that your two locus are probably on different chromosomes. They're very far apart. In our example, we got 0.11. So do we think it's close together or far apart? We probably think it's close together. Okay, because we said if it's far apart, our probability should be 0.5, and we got 0.11. Okay, but imagine this. Imagine when you did your calculations, you got 0.49. So you think, oh, maybe it's 0.5. Maybe it's close enough to 0.5 that we can say it's on separate chromosomes. So we need some way of knowing is my answer so different to 0.5 that I can say, no, they're probably close together on the same chromosome? Or is it close to 0.5 and so I can say, oh no, they're on different chromosomes? So we decide this by using the Z-score. Okay? If the Z-score is very big, then we can say, yeah, this is probably right. If the Z-score is very small, we think, oh no, maybe it's actually more like this one. In other words, this Z here lets me decide if it's this, which is what Mendel would say, or is it this, the true one, which is this is the one that we got from the data or from the experiment. Okay. Now, what do I mean when I say big? Well, in the question, I said this follows a normal distribution. Now, have you done confidence intervals in normal distribution? Do you know this thing plus or minus this thing? No? Okay. Have you done the table like this, the bell curve? Yeah? Yeah, something like this. This starts at 0. In your table book, what's the biggest value you can look up? I think you can go as far as maybe 3 or maybe 4. But then after 3 or 4, you can't look it up. The table book finishes. And this is because the numbers are so extreme and so unlikely that you don't need to consider them. So my point is, because I got a -10, that is so outside of what you would expect that you can say, oh no, this is a big value, meaning that we can trust this number. I suppose if I want to put it simply, the Z, if it's big, implies that you can believe your P is equal to 0.11. But if the Z was small, then you would doubt, you would not believe your P is equal to 0.11, and you think that maybe it could actually be 0.5 after all. It's a way to test if your P is believable. So in this example here, are 0.11 believable or not believable? It's believable, which again, this is like another situation that contradicts Mendel's sort of genetics. Okay. Summary. So, what's our summary? Okay. Mendel did his experiment with the P's, right? And the Punnett square. And from this Punnett square and the experiment with the P's, you can calculate the ratio you expect to observe, which we said is 9, 3, 3, 1. So you do a similar experiment, except instead of using P's, you use flowers or whatever. And instead of getting the 9331, you didn't get the 9331, and you did a chi-square test. And your chi-square test confirmed that you should reject this. That was basically the first half of the assignment. The second half was also, according to Mendel, the probability of recombinance should be 0.5. However, in your experiment, you got probability of recombinant was 0.11. And you calculated the Z value, the lowest Z, to confirm that you were correct in your 0.11. So basically both the tasks very conclusively show that, at least in this situation, that Mendel's theory doesn't actually work for your genetics. Do you get that? Yeah. So just, maybe if I could just draw, could I go to the side there? So this is how this works in the biology. You start off with a hypothesis. So in this case, the hypothesis, or the theory, I suppose, Mendel's theory, okay? Then you collect some data, and then you do some kind of test. And then the result of the test makes you accept or reject the original sort of claim. So in the first task, the theory was we should get 9, 3, 3, 1. And then the data we collected, and then what was the test that we did to check? We did what's called a chi-squared. Okay. Then in the third task, according to Mendel, the theory says the probability should be 0.5. We calculated as 0.11, and the statistical test that we used was what's called the LODZ score. And then in both cases, we rejected Mendel's theory. Now, does anybody know why Mendel and this is quite different? Or what Mendel did or didn't do? Not that his theory was wrong, but his theory was quite a simplified version of reality. Does anyone know what was sort of not the trick or the cheat, but the catch in his experiment with the bees? I don't know if Colin talked about this. It has something to do with chromosomes. Say again?
Maybe like something he was trying to prove.
Yeah, he was trying to prove something, and he very deliberately did something that sort of confirmed what he suspected. In other words, he chose an experiment that was very convenient for what he wanted to prove. Does anyone know? I don't know if Colin talks about this. So in Mendel's experiment, with the peas, yeah. Yeah, but there was something very deliberate about what he did. Of course, with the peas, you can look at any traits and breed for any traits. But all the traits that Mendel studied for his peas, they were all on different chromosomes. So this means Mendel's data was data for traits that were always on different chromosomes, which means that's why he got P at 0.5. That's why his ratio of 9:3:3:1 works. Mendel's theory is for a theory when all the traits are on different chromosomes. But what people after Mendel discovered was some traits, when they're close together on the same chromosome, they don't produce the proportion you would expect from the children. Yeah. Yeah. Does Colin talk much about this in the genetics? I don't know. Yeah. Does this sound familiar? Yeah. So in real life, many traits are on some chromosomes or different chromosomes, and they actually can interact, and you don't get the pure result Mendel expected when each trait is on its own chromosome. So in Mendel's experiment, it's very idealized. You know, everything's nice and simple. This trait is on this chromosome, this trait's on this chromosome, and they combine 50% of the time, or don't. You know, very simple theory. So your coursework rejects this simple theory, but of course everybody knows this. You're not doing breaking research. But the reason I wanted you to do this is if you study any kind of genetics course or any kind of science in biology, they'll have you doing these types of statistics. So this is kind of giving you a preview of what you might do next year. You're all doing something kind of biology next year, aren't you? Or what? Say again? Nursing, yeah, okay, so you'll do a genetics, something, yeah, so genetics you'll probably do as well, yeah, and
Forensic science.
So you'll probably end up doing the most on genetics, I would have thought, right? Because isn't DNA like sort of a
Depends
critical...
on which branch and which you specialize in. But
okay, and what are you thinking of?
I'm going to just take a general forensic science, and then I might specialize in biology, like forensic biology. But
okay. Even if you don't, I imagine whatever path would have a sort of a good 2-semester course on genetics, because, you know, being so critical for it. Yeah. Okay, so when is this due now? Tuesday. Okay, so you have the weekend to type everything up and to do the calculations for your data and submit it on Tuesday then. Do you feel like you can get this ready for Tuesday? Everything is okay here? Yeah. Okay, so we'll wrap it up there since there's nothing left to do. And next week we'll go back to the exam questions. Where did we finish? Was it we were doing algebra? Yeah, so will we move on to something different? What do you think will be?
I actually don't understand calculus. So
We'll move on to calculus then, derivatives and integration next? Yeah, okay. We'll take that up then next week. So
Thank you.